Hello. Suppose that I would like to calculate the period of a pendulum. So this is a pendulum and it swings. And I would like to calculate the period of this pendulum. But this time, not for small angles necessarily, but for any angle. So the history of the pendulum is that Galileo Galilei found that for small angles, the period of the pendulum is 2 pi square root of L over G. So this is interesting because the period of a pendulum is given by this relation, and it is true irrespectively of the initial angle. So for small angle or perhaps even twice as much, it will be roughly the same number. So that was quite interesting. It is also independent of the mass of the pendulum. Now, let me briefly mention how we arrive at this equation. So at school, what we learn is that if we analyze the forces on the pendulum, if this angle is theta, the force is the relevant force is mg sine theta, and Newton's second law is that mass times acceleration. The acceleration is the L time the angle double dot is the angular acceleration equals minus mg sine theta. For small angles, we can write minus g mg theta. So we found the following equation. Theta double dot is minus g over L theta, and the solution of this differential equation is as follows. First, let's call omega equals square root of g over L. So we can see that a solution to this equation is that theta is theta max sine omega t, and from this relation we see that we can write it as theta max or theta m, theta max sine 2 pi over capital T small t. So we learned that the period is indeed 2 pi over omega. So that's easy peasy. And now let's see what happens when theta max is not small and we cannot make this approximation. Okay, so the way to solve this problem is to analyze the energy of the pendulum at a given theta. So this is a pendulum, and the total energy of the pendulum is its kinetic energy, half mv squared, plus its potential energy. Now, the velocity is the x dt, which is d dt of L times theta. It's the arc, and I will denote it by L theta dot. The relevant height h is L times 1 minus cosine theta which can also be written as L 2 times sine square theta over 2. So the total energy is half m L total dot theta dot square plus m g L 2 times sine square theta over 2. So that's the general energy. It is conserved, and therefore we can equate it to the same expression, but at the maximum theta where the velocity is 0. So this is also equal to 0 kinetic energy plus mgl 2 times sine square theta m over 2. So now I have an expression for the energy. I can equate the two sides of the equation. I can divide by the mass. The mass cancels. That's good because the mass shouldn't matter. It cancels the same mass that appears in the kinetic energy and the potential energy, and cancels, and therefore it's irrelevant. That's expected. It's the same period for small mass or large mass. So then what else can I do? I can simplify a bit the expression by dividing by the mass, canceling the mass, and by L square. So half theta dot square, I'm dividing by the mass and L square, plus G over L 2 times sine square theta over 2 equals G over L 2 times sine square theta max, theta m is theta max over 2. So we arrive at a very useful relation that theta dot square, by moving this to this side and multiplying by 2, we learn that this is 4g over L over L. It's difficult to write over L. Let me try to do something, right? G over L. And what do we have? Sine square theta max over 2 minus sine square theta over 2. So this is essentially the way to solve this problem, because theta dot is 2 omega, and omega is simply square root of G over L. It's just a name. I define omega as square root of G over L. Of course, we know that this is the relevant omega for small angles, but for the moment, this is just a definition. Square root of sine squared theta m over 2 minus sine square theta over 2. And now let's see how this relation helps us to find the period. Okay, so now it's kind of straightforward. We can write d theta over square root of sine square theta max over 2 minus sine square theta over 2 equals, what do we have? 2 omega dt. And now we can integrate both sides. Now, what I will do, I will do the integral over a quarter of a period. So let's say from this point to this point. So it swings, and let me select this segment, which is essentially t over 4. So in the right hand side, I will have 2 omega capital T over 4. And the right hand side, the left hand side will be from 0, the angle 0, theta equals 0, up to theta max. So that's more or less the end of the story, because all I need is to calculate this integral. It's not an easy integral. We can simplify it a bit by selecting a variable x, which is theta over theta max. And then the left-hand side is the integral from 0 to 1. Now, instead of d theta, we have theta m outside, integral dx, because d theta is dx times theta max, over square root of, what do we have here? Sine square theta max over 2 minus, and then what we have here is sine square theta max over 2 times x and that is half omega t. So this is more or less the end of the story. What else can we say? Well, we can consider some special cases. We can do this integral numerically. We can do some things. Let me show you what can we do with this integral, like two or few examples. So we have a relation as follows: half t omega equals theta max, the integral from 0 to 1 dx square root of sine squared theta m over 2 minus sine square theta m over 2 x. The first thing I would like to show is the small angles approximation. So when theta m is much smaller than 1, we can use the approximation that sine square of y is y squared. And using this approximation, we arrive at half t omega equals theta m integral from 0 to 1 dx. And what we have here is square root of theta m over 2 squared, namely theta m over 2, and 1 minus x squared. So this is 2 times this integral, which is 2 times arc sine 1, and this is 2 times pi over 2, namely pi. So the period t, when the angle is very small, for small angles, is 2 pi over omega. Okay, so good. We recovered the old result by Galileo Galilei that for small angles, the period is 2 pi over omega. And so this is 2 pi square root of L over G. Fine. But what happens in general? Well, in general, we have this formula. How do we use it? Well, we have to substitute some angles theta m and evaluate this integral numerically. So, an example, let's consider very large angle. Let's consider the angle theta m equals roughly 1.5. Why do I choose 1.5? 1.5 is very close to the maximum angle, which is pi over 2, right? So theta m, the maximum will be pi over 2, which is roughly, it's a bit above 1.5. Let's see what will we get for the period when theta m is 1.5. Well, we have to do this integral. I have to 1.5, the integral from 0 to 1 dx, and then square root of sine square 1.5 divided by 2, which is 0.75, minus sine square of 1.5 over 2x. And we can calculate this integral numerically. And the result is that the period turns out to be, instead of pi, the number that we get is close to 4. So it is roughly, not exactly 2 times 4 omega, or roughly 8 square root of L over G. So instead of 2 pi, we get 8. So what we see is that as we increase the angle, the period increases, and it is not independent of theta, but there is a deviation. And the deviation is, or in general, the range is between 2 pi and 8. So to conclude, let me conclude. The conclusion is that the general relation is this. Thanks.